So we have the world sheet theory and the space-time theory. Let's do it for the closed strings. Now, what are the fields that we have here? Can anyone tell me? What are the fields in this theory? The what? Excellent, yes. Just a bunch of scalar fields. Okay. And the theory is defined. So this theory, these are the fields. And the theory lives on R1, 1. Okay, very good. What kind of theory we have? What are the symmetries of this theory? It's a CFT, yes. Very good. Okay. Now, what we discover here is that we also have some fields in space-time. And what are the fields that we have found up to now in space-time? The dilaton, the B field, yes, very good. And of course, our graviton. Well, the graviton is hidden inside here, right? Now, we also talked about, even in the open string, we also talked about a tachyon. Where would the tachyon go? There or there? There, excellent. So we also have the tachyon. Okay. Is this theory conformal? Nope. Okay. And what is the theory? Well, the action for this theory is, and this theory lives in, we decided that it had to live in R1, 25. And this was the action in space-time. Now, the equations of motion coming from this action happen to be what on this side? Very good. So the field equations ended up being here the conditions for the vanishing of the beta functions. Now, this action, just like this, of course, is missing something. It's missing a dimension-full parameter, which we can call, people like to call it something like this. But of course, this dimension-full parameter, the only thing it can be, it should be related to alpha prime, which is the only thing that we have in our theory that has dimensions, right? Let's not worry about that for a moment. Is this exactly the Lagrangian that you studied in GR? What's the difference? Say no. Yeah, that looks kind of strange, right? This thing here. Well, but you see, that's the thing that comes naturally from the equations of the string of the string wall sheet being conformal. So people call this form of the metric, they call this a string frame. Even though there is nothing that looks stringy, I mean, this is just looks like just a regular action. When you have this factor of the dilaton in front of this scalar field, then you say that this is a string frame. Just to remind you, this H, remember, this was a three-form, and it's a curvature of our two-form gauge potential. So this is our gauge potential now. Very good. Now, if we use a field redefinition, okay, we can go to the action you know and love. Okay. And people give a name to this one. Sorry? Yes, yes. Forget. Yes. So this one also has a name. People call this one the Einstein frame. Okay. So be careful when people give you a metric or give you something, you should always ask if it's in the context of a string theory, if what they are giving you is in the string frame or in the Einstein frame. Okay? Very good. So now in the string frame, there is something interesting that we can notice already. Imagine that we shift the dilaton by a constant. Say the dilaton acquires some expectation value, and there is some fluctuation, which we call the field again, right? So what happens? Well, clearly, nothing happens here. These are derivatives. And what happens is that we pick up a factor from the overall exponential. So our action will now have a factor of the form 1 over 2 kappa 0 squared e to the 2 phi times the integral okay? So somehow we can shift the coupling constant of the theory if we just shift the dilaton by a constant. Okay? So this is why we think about this as being the coupling constant of the theory. Well, or more precisely, I think I want to say that this is a coupling constant of the theory, and then the action has a factor in front of the form 1 over g squared. Okay? That looks more canonical. Very good. So now in terms of this coupling constant, we can do perturbation theory here, right? Now, of course, this action that we got here is an action that has, if we think about it, it should be something that has an alpha prime. And in principle, if we keep going computing, remember, we computed the beta functions only at one loop. What is the, yeah, so this is a good question. So this would be the coupling constant on this side of the blackboard. What is the coupling constant on this side of the blackboard? What is it? Right. So we can, in principle, we would say that it's alpha prime, right? This is dimension full. Really, we should write some combination of alpha prime and some curvature so that it's dimensionless, okay? But this, roughly speaking, alpha prime will be the coupling constant here. And remember, the equations we got over there, or the equations that led to that action, were just the leading order term in a perturbative expansion in alpha prime. Say you're very, very strong and enthusiastic and say, well, I cannot wait to see what the two-loop correction to the beta functions would look like. So you sit down and compute them. So the beta functions here will have higher order corrections, right? At 2 loops, we will expect to have something like this here. And whatever that is will also be equations of motion or field equations for these fields, and we will have to add them here. Okay? So this action is just a leading order in alpha prime. Okay? Very good. But still, on this side of the story, we have this coupling constant, and we can still compute 3-level scattering in perturbation theory, if we want, of gravitons, and we can compute 1-loop corrections and so on, 2-loop corrections in this coupling constant. What could they correspond to on this side of the story? So that's the question we want to answer now. So just the action we have there, we said is leading order in alpha prime. So that's an effective action which is valid when you have very small curvatures, okay? Long distances and small curvatures. So that action should be a very good approximation to what the string is telling the space-time to do. But nevertheless, we can still compute, we can still do perturbation theory in G. In other words, we can compute the scattering, say, of gravitons. So these are gravitons. And get something that looks like a 3-level. So I have to find a good notation for that. So we can say 3. So we can put this 1 over G squared here. So there will be a coupling, a factor of G squared if we compute a 1-loop. G to the 4th, we compute a 2-loop. So how do I'm going to be in trouble if I keep doing this. So maybe I'll just say 1 loop, 2 loops, and so on. Okay? So I know, everybody tells you don't do perturbation theory on an effective action. But, well, remember, we have alpha prime, okay? So we can control what we're doing. So this is the perturbation theory of the full action to leading order in alpha prime. So what could that correspond to in this, on this part of the theory? So I didn't tell you, but the way you compute interactions from the world sheet is the following. The first step, so let's compute interaction or scattering. Of strings. So the first step is that you make the theory Euclidean so that you can use all the machinery of CFT. So we could do it, right? But you already took a course on CFT, right? So if you have a CFT, what is the next thing that you have to do? Well, you have your CFT. What kind of operators are the relevant, the important operators that you have to study? Do you remember the name of those operators? Yeah. You construct the vertex operators. Okay. And then, well, if we make our theory Euclidean, the simplest world sheet that we can have is actually a sphere where the vertex operators will be inserted somewhere on the sphere. Okay? And you know that this looks like this because we have a conformal field theory. If it wasn't a conformal field theory, it would really be something where we have, or the original picture where this thing starts from is states that are coming in, interacting, and coming out. Okay? But using a conformal transformation, we can make them We can make the tubes to be very, very thin and infinite in length, and we can replace them by the vertex operators. Okay? Now, from the point of view of the world sheet, this thing here is the space-time where the theory lives. Okay? And the way you compute this contribution to the scattering amplitude is actually by doing the partition function of the string put it here. Well, with insertion of the vertex operators. Okay? But now this integration is done on a world sheet that looks like, or that has the topology of a sphere. Okay? And how can we tell that that happens there? Well, because imagine that we have turned on a dilaton background. Remember, the action or the way the dilaton couples to the string is the following. We said it was something of the form d2 sigma, phi of sigma, the two-dimensional Ricci scalar times square root of minus h. Okay? So we had to put this here in the action. Now imagine that this guy, just like in this case, acquires an expectation value. So it's just a constant. It's a number. So this guy is a number. Let's replace it by its expectation value. Remember, the goal now is to match this perturbation theory here with something that we do on the world sheet. Okay? So we have this guy. This is in the action e to this. There is a factor of 2 pi, perhaps. Now, once we do this, what do we get? We get e to the phi, expectation value, times, this is now a number, doesn't depend on sigma, or tau, so we can pull it out, and we get integral this integral over here. Remember, we wrote this the first day. Yes? Yeah, I don't have to remind you because I didn't tell you, right? I simply declared that that was true. So to derive that this is the correct coupling, you have to construct the vertex operators and exponentiate them, okay? But we're not doing that. However, what I did tell you, I think it was during the first lecture, was that we started with a theory that was a theory of gravity in 2 dimensions, but somehow we did something and we never wrote this term anymore. Why didn't we write that term anymore? Because it's a topological invariant. And it was equal to what?
Euler characteristic.
Yeah, so it was the Euler characteristic. Of what? Well, of the topology of the world sheet. So we have this guy here. So let's not worry about let's not worry about these vertex operators as being punchers. Let's just worry about the topology of the sphere, because these vertex operators are actually here. Okay. So this integration is really over a sphere. So what is the Euler characteristic of the sphere? Is 2. So if we have a sphere, the Euler characteristic is 2. Okay? So from there, we get a factor of the form e to the... Okay? Very good. Now, the Euler characteristic, remember, our goal is to find something that looks like this, an expansion where we have g, g squared, and so on. Okay? So,
a question?
Yes.
What kind of vertex operators would you have here?
What kind?
What do they look like explicitly?
Well, say for the graviton, you can have something that looks, well, for the tachyon, you have something that looks like, it would be something like x dot x of k mu, something like this, where k is the label of the. So this is something that will generate the tachyon. If you want to gauge boson, then you have to put the polarization vectors. Polarization vectors times these guys. If you want a graviton, you have to put the polarization tensors times these guys, and so on. Okay? But once again, we're not going to compute interactions, so we're not going to worry about what vertex operators you want to put in there. Okay?
Okay.
Yes?
To be sure, was the reason we integrate now the sphere was because we fit in and both are?
Yes, that's right. But, well, we got a sphere, but if we now have a compact Riemann surface, why choosing a sphere? Is there anything that is special about the sphere? Not really. We chose a sphere because it was the simplest possible one, right? But we could have chosen something more interesting, right? We could have chosen a torus. Why not? If we did that, we would get chi equals to 0, right? Now we can keep going and make more and more complicated choices for our world sheet, and so on. Of course, in general, you know that this is a genus. If we have a surface with genus G, then the Euler characteristic will be 2 minus 2G. Okay? Now, so I'm probably missing a minus sign in my definition. Right. When we compute this thing without this minus sign is the Euler characteristic. But remember that we had this minus sign here. So I have to put this minus sign. Okay? So the contribution for the sphere is minus e to the minus 2 phi. Now, using the definition I made there for G, remember this is not the genus. I should have called this differently. Oh, I know. Let's call it GC. It's a coupling constant of the closed string theory. Okay? That will make it different from the genus. So this thing is 1 over G squared, GC squared. Okay? So what we see is that the perturbative expansion on that side will correspond on this side, or the natural conjecture is that on this side, it will correspond to an expansion in the topology of the world sheet. So whatever scattering we're doing, the computation over there on this side is going to look like 1 over G squared C times our partition function with the vertex operators inserted, computed on a sphere, plus, remember now this one has a 1 over G squared C as an overall factor, so I'm putting it out. The torus has nothing, but since I pulled this out, I have to put a G squared here. The genus 2 world sheet had a G square. Pulling this out, we have to put a G to the 4th. And this is how we complete computation. Now there is something interesting here that people realized very, very early on, which is the following. In these computations, if you're doing quantum field theory, how many diagrams you think you have to do, how many Feynman diagrams you have to compute in order to compute this 4-particle amplitude? You have 4 particle amplitudes of gravitons, even in 4 dimensions. Imagine that somebody told you to do it in your GR course, just for fun. Say, mix a little bit of quantum field theory with GR, right? And compute a 4-particle scattering of gravitons. How many Feynman diagrams would you have to compute? How many? Yeah, there will be many, many of them, yes. But it's not, yeah, there are, it's just GR. It's just GR. So you linearize GR, and then you compute it, okay? So there are many diagrams, but not only there are many diagrams, but also the vertices are complicated. They will have many, many terms. So this computation can actually be a very, very long computation. Now, how many diagrams do we have to compute in this case? Well, there is just one. There is only one diagram, really. It's this one. At one loop, the number of diagrams is incredibly large. I think in this case, it would easily be of the order of perhaps thousands or tens of thousands, okay? And in this case, just one, okay? So people realize the power, perhaps, of computing scattering amplitudes using a string theory method. So that was a small industry in the 90s. So people realized that perhaps one can use the power of a string theory to reassemble Feynman diagrams. So how come that these guys, just single terms, just one diagram can produce so many, can be equivalent to so many diagrams? Because that's something that people check. That if you do this computation to leading order in alpha prime, you should get the same answer as what you get there. If you do this one to leading order in alpha prime, you should get the same thing there, and so on. So how does it happen that these guys will end up giving you so many, being equivalent to so many Feynman diagrams? Leading order in alpha prime means that you have to take alpha prime very, very close to 0, right? So what happens to the tension of the string? Remember, the tension was?
1 over 2 pi alpha.
So if you take alpha prime to 0, the tension is very, very large. And a string with a very large tension would look like what?
At all?
Would look like?
No.
A what? What do you say?
If it's very, if the tension is big, then it's not a very.
Then it's very, very hard to pull it, right? So it would look like what somebody said it already. It would look like a point, right? Yeah, it has so much tension that it's very, very hard to pull it out, to stretch it, right? Well, if it looks like a point, then different regions, what you're going to get, say, from this diagram, or from this diagram, say, let's look at this one. This one is more fun. So what happens is that when the tension is very, very large, this thing will only receive contributions when this Riemann surface degenerates. How can it degenerate? Well, it will degenerate in such a way that, say, these guys come in, and now this thing pinches, and it looks like something like this. Now it looks like a particle, really, okay? Or it could also degenerate in a way that, say, these two guys come out of here, and you produce something like this. So this Riemann surface can degenerate in this form. And in any other form that you think possible when you take this alpha prime going to 0 limit. And that's those corners in the moduli space of the Riemann surface are precisely in one-to-one correspondence with the Feynman diagrams that you can have. Okay? Well, in any case, this is not really important. I just said it because people were using this as a computational tool. Okay? In fact, some of the first gravity amplitudes that were ever computed were computed using string theory. Okay? Yes.
I didn't really understand how you got into that inequality.
Yeah, we didn't get it. We postulated it.
But you started with saying something like the coupling constant should be related to.
Yeah. Oh, yeah. So what I said was that if we have different topologies for our world sheet, the partition function will pick up an overall factor. You see, the partition function on the sphere will pick up from this term an overall factor of 1 over GC squared. Right? So this is a partition function without that factor. I'm putting it out. Yes?
So that requires that your measure has just divided somehow by all the equivalent possible. You're integrating over DH, so over all geometry.
No, remember, in GR we integrate over all geometries, but people don't usually integrate over all topologies. Here we're actually doing what we are supposed to be doing if we were doing GR seriously, which is to integrate over all possible metrics and integrate and sum over all possible topologies. So in fact, this would really be an honest GR computation in 2 dimensions.
So the measure would be somehow modulo isomorphism.
Yeah, of course, there is tons of, well, we know in this particular case, we can even integrate out the metrics. So there is tons of diffeos that we have to divide by. Yeah, no, that's true. I didn't write everything in detail. So there are many things we have to divide by. This partition function as written like that is not well defined. That's true, because we have a gauge redundancy, right? But that's a very important point. In GR, people usually take a fixed, sometimes people don't take a fixed background, but they take a fixed topology. But that's cheating too, right? You're supposed, if you're really going to do things seriously, you have to allow any topology. You have to sum out all topologies, all metrics, everything, right? So here we're actually doing that. So if you wish, this is the full computation in quantum gravity in 2 dimensions. We're supposed to sum over all possible topologies. And what we're finding is that this sum, or this perturbative, this is not a perturbative expansion, right? This is an expansion in topologies. And each one of these diagrams represent a full computation in a partition function. Matches this perturbative expansion. Okay? Very good. So that's all I want to say. In fact, it was probably more than what I wanted to say about the connection between the perturbative expansion of that and the quantum gravity theory in 2 dimensions. Okay? Very good. So now we're more or less convinced that we are on the right track. Yes? You mean for taking, no, it's not cheating. We're doing exactly the same thing on both sides. So if we were doing something different on that side, we would also do something different on this side. Yeah. Well, remember, phi is a background field. So what we're asking is how does the action of the stream looks like on that background, right? And we're taking the background to be constant. And it so happens to be the same constant as the one we're choosing on this side, okay? Of course, there are cases where, first of all, there are cases where the dilaton is not constant, right? And then one has to be very clever to know what to do on this side. And there are cases where the dilaton is such that it's very, very large. G is very large. So what do you do in those cases? You don't have a perturbative expansion, right? Because if G is large, you are out of luck. You don't have it there, you don't have it here. So people thought that for a long time that perhaps we would be stuck with perturbation theory forever, right? Because on this side, how can you even start thinking about doing something that is not perturbative in G? There, well, you could try perhaps imagining something, but in any case, we know that that theory is just an effective theory. That theory has divergences. As written, it has UV divergences, right? Because it's just an effective theory. We're missing all the alpha prime corrections. Well, in the 90s, people started to discover something very amusing. We haven't talked about that, but there are different string theories. And people found that magically, some of them started to be equivalent. You could actually show that when the coupling of one of the theories was very, very large, the description that you got for that theory, or the theory, ended up being equivalent to another theory when the coupling was very, very small. So somehow the string theories were very smart, and they were saying, well, if you don't know how to compute me, because I have very, very strong coupling, don't worry, I'm equivalent to another theory with a very weak coupling. So you can do weak coupling computations there and get answers for what I want to do. Okay? So those are the dualities that were discovered in the 90s. But remember, we're barely in 1980 something. Okay? Okay. So what do we want to do now? We want to keep going towards a theory of quantum gravity. Of course, the theory of quantum gravity is a theory where, the actual theory of quantum gravity that describes nature is something that is supposed to produce a macroscopic four-dimensional spacetime. Not only that, it's also supposed to have the standard model. At low energies. Well, we don't seem to be doing so well, right? Because first of all, we have many more than 4 dimensions. So where are we? Well, just so that we feel a little bit better, say we need something that is mathematically consistent. So in mathematical consistency, we're almost there. Maybe we can say we're in good shape there, okay? Because we have this conformal field theory that is very powerful. And as we discussed yesterday, it will allow us to get away from the UV divergences, okay? So in terms of mathematical consistency, we're in reasonably good shape. In terms of 4 dimensions, we got instead 26. So that doesn't quite look very good. And in terms of the standard model, well, what kind of fields we have? We have a gauge boson, a massless gauge boson. We have tachyons, and we have these other funny fields, but they are all, whatever we have are all bosons. Okay? So we are missing fermions. So you have to go down to 4 somehow. So we have bosons, we're still missing fermions, and somehow we have to find a way to go from 26 to 4 dimensions. Well, quite nicely, this is something that already was something that people started to explore very early on after GR was discovered. Kaluza-Klein started to play with the idea of unifying gravitation and electromagnetism as a theory that comes from 5 dimensions, okay? So the notion of higher dimensions and compactifying them, or giving a topology in such a way that the extra dimensions were small circles, is something that is almost as old as GR, okay? So perhaps we can keep going and not worry about this and say, well, maybe there will be something similar to this that will help us out, okay? But there is a more pressing problem, it seems, which is that we're missing fermions, okay? So how do we put fermions in? That is a question we want to start answering now. Well, the fermions we are missing are fermions where? On the worldsheet or the space-time? We're missing them in space-time, right? So how can we start putting fermions in space-time? Or how can we get fermions in space-time? So let's do open strings. Let's go back to our favorite action. And ask, how can I add something to this action to produce fermions in space-time as part of the spectrum when I quantize the theory? Well, the answer to that question is that I have no idea how to do it. I mean, if that was the question, I would have no idea, really. But instead, you can ask for fun, well, if you want fermions in the space-time, you should start by adding fermions on the worldsheet and see what happens, okay? Now, remember, our x mu's are scalars, okay? And the mu index is a vector index in space-time. So we can do the same thing. By analogy, we can say, well, maybe what we should add to this action is something that will be a fermion. Well, this refers to the statistics, but we know that it has to be a spinor. In terms of representation, it's a spinor under the Lorentz group of 2 dimensions, under the 2-dimensional Lorentz group. And it's natural to consider as many of them as we have of these ones. After all, we want to make a connection to space-time, to the configuration space. So we should also introduce as many as we have of these guys. What action do we have to write? Well, that's canonical, right? So we know exactly what we have to write. It's something of this form. Now, what do I mean by this? Well, you probably have seen in quantum field theory, you know what this means. In general, this works in 4 dimensions and in any number of dimensions. The Dirac-Lagrangian is the same. Well, in 4 dimensions, we have, in order to write down the Lagrangian, we have to introduce the gamma matrices, right? The Dirac matrices. So here, we're going to introduce the analog, and we're going to call them the rho matrices. So these will be matrices, and they satisfy an algebra, which is a Clifford algebra of the space-time that we're dealing with. So this is our space-time metric, okay? How many rows we have? Well, we only have 2. And it turns out that there is just a 2-dimensional representation of this Clifford algebra, and that's the one we're going to use. Okay. In terms of this is our del bar operator, or del slash, I guess, operate. Very good. So what is our psi bar? Well, it's something that looks like 1 over rho 0 psi dagger. Sorry. Let's put an I here. Okay. So today you're going to see, is that today? No. So So the tutorials are, so you're going to have one tutorial today. Oh, you had one yesterday. Oh, great. I see. So that means that you saw it already. So yeah, that's even better. I thought that it was going to be today, so you didn't know about this. So you're all experts in spinors now. So you know that there are spinors. When we have spinors, we can impose different conditions, right? We can ask for the spinors to be Majorana. We could also impose, so these are conditions we can impose on spinors. We could also impose them to be Weyl. Okay? And you can ask, well, can they be Majorana and Weyl at the same time, right? So those are two different conditions. So in 4 dimensions, can we impose both conditions at the same time? Can that be done? No? How about in 2 dimensions? 2 dimensions we can, so that's great. So we're going to do it. So we're going to ask our spinors to be Majorana. And in order to impose that they are Weyl spinors, or how to get Weyl spinors from the regular Dirac spinors, what do we have to do? We have to construct the analog of gamma 5, right, in 4 dimensions. So in this case, it would just be, let's call it rho 2, right? Which would be rho 0 times rho 1. And this matrix looks like an I where? Okay, so this is our gamma 5. Really, these two here will look confusing. It looks like rho square. So let's just keep it as rho. Okay. Sorry? Yeah, that's true. Yeah, we have been called gamma 4. Yes, that's right. But even rho 3 would still look funny. It would be like, yeah, we know that rho 0 is not rho to the 0 because it would be stupid. But and rho 1, yeah, it's also, yeah, but
it's the same argumentation for gamma 5.
yeah, I know, but I don't know. It doesn't feel right to call it rho to something. In any case, here I'm going to use the power of the lecture. I'm giving the lecture, so I choose my notation. You're taking your notes, so you can write whatever you want in your notes. There is no democracy about the notation that I'm going to use. Okay. So remember, what we do in order to decompose something in Weyl spinors is that we ask the object to be an eigenvector of rho with eigenvalue plus or minus. So it's clear that what's going to happen is that our 2-dimensional spinor, the top component will have one chirality and the bottom component will have another chirality. So we can just write our Dirac spinor as something that has minus chirality and something that has plus chirality. Okay, so these are our Weyl spinors. Okay, now what is the action written in terms of these Weyl spinors? Well, we just plug them there, okay? But there is something really nice that happens if we choose Lycon coordinates. Remember, our Lycon coordinates are defined to be tau plus minus sigma. Okay? So here is a small exercise for you to show that when you write this in Lycon coordinates, something really nice happens. And here I'm going to use that these spinors are also Majorana, okay, to simplify my action. So I'm going to write only the psi part of the action, and it's going to be 1 over 2 pi I, so 1 over 2 pi alpha prime integral d2 or sigma plus d sigma minus. We're going to have psi plus. Now it depends on how lazy I am. It depends on the, well, I can put the mu index explicitly and just contract it like that. Or remember, we also have this. We also had this notation with a dot, just to save a little bit of notation, right? The dot means the contraction of the mu indices. Isn't that very convenient? You see, the pluses came out with the derivative with respect to the sigma minus, and the minuses came with the derivative with respect to the plus. That looks very, very nice. So this is our action now. And in the last 5 minutes of the lecture today, we want to find the field equations and the boundary conditions. And remember, we're doing the open strings. There. Okay. So let's vary our action. Let's not worry about the 1 over 2 pi alpha prime. Let's put this at 2 sigma squared there. And we have the variation of this dot derivative plus psi plus variation of this guy plus variation of minus and psi minus okay, so the next step is a usual step of taking this guy, running it as the derivative of the variation, and then integrating by parts. So we integrate by parts, we get minus plus del minus of psi plus. Okay, that's what we get here. There is another minus here. The same thing for this guy. We integrate by parts and we get plus psi minus plus psi minus. Sorry, yes. Sorry, this is a delta, right? Is that what you were saying? Very good, thank you. Yeah, it was a little bit funny. Okay, very good. So these are the guys that will give us the boundary conditions. Now we have to combine this with this, and we get? Very good. These two guys give us 2 times and the reason is that they anti-commute, right? The same thing for these guys here. So we'll get these 2 guys, okay? So the answer would be something of the form, these 2 guys here psi minus, and then we get the boundary conditions. So the field equations are simply very nicely that the psi plus has to be only a function of sigma plus, and that psi minus has to be a function of only sigma minus. So finally, let's look at the boundary conditions. Okay. So what are the boundary conditions? Remember, we do the same thing as we did in the bosonic case. We separate this, and we say, well, this gives us a term which is of the form minus derivative with respect to sigma, psi plus a term that depends on tau, which we are not going to care about, right? Because in the integral over tau, this will give us contributions at tau minus and plus infinity, and we are assuming that the variations vanish there. So this thing will not be important. From this piece, we get a plus sigma minus this variation plus derivative with respect to tau, and once again, this one we don't care about. So we only have to worry about the derivative with respect to sigma. So the boundary terms will look like an integral from minus infinity to infinity d tau, integral from 0 to pi d sigma of this derivative with respect to sigma, psi plus delta psi plus derivative with respect to sigma, psi minus delta psi minus. So this thing gives us, we will get psi plus delta psi plus evaluated at sigma equals to pi, right, with a minus sign. And we will also get a contribution from this guy at sigma equals to pi, but it will come with a plus sign. Minus a contribution at sigma equals to 0. Okay. And all this thing integrated in tau. So we want these things to be 0 independently. Okay. So those are the conditions we have to impose. So what kind of solutions can we find? Well, note that we can also write these conditions as saying that this guy, or these conditions would also be satisfied. Let's write it there because I cannot move this blackboard. This is the one behind. So let's do it here. So in order to satisfy those conditions, we can declare, or we can set, that psi plus at pi has to be plus minus psi minus at pi. Okay, it can be any of them because we have the product of two factors. So we can actually choose plus or minus. On the other end, we can have the same thing. Okay. So now, a relative sign on these conditions will not have any physical effect because we can always rescale all the guys. We can always rescale all the psi minuses. say, by a minus, or all the psi pluses, and nothing will change, okay? So one of the relative choices of signs on one of the two conditions is redundant, okay? So we can always select, so one is redundant. So we can just choose plus as our convention. Okay? And these two are actually physically different. So we have two ways of imposing boundary conditions. And the two ways have names, and that's what I'm going to tell you now, and we're going to basically stop there. If you impose that this is true, okay, if we choose the plus sign, well, let's put it explicitly here. If we choose the plus sign, these are called Raman boundary conditions. And, well, I already told you what this is, so we can just choose our conventions here and erase this. And the other possibility is with a minus sign. And these ones were discussed by Neveu and Schwartz. Okay? So if you want, as a little exercise for next time, solve the field equations, once again expand in Fourier modes, okay, and impose the boundary conditions. Impose the Raman boundary conditions and impose the Neveu-Schwartz boundary conditions. So what we're doing with the fermions, in this case, in general, in this theory, is called the RNS formalism. For obvious reasons. Right? Okay, very good. So, any questions? Yes?
Do you have any intuition of what is happening or why with the fermions you can have these two boundary conditions that some people are doing?
Well, it's exactly the same physical reason that goes behind saying that it's basically the same reason as saying that the spinor is a double cover of the usual representation of. Yes.
Does it have to do something with chirality?
No, it just has to do with the spinor representation. Yes. Oh, because they are evaluated at different points. Otherwise, it would be a funny. Remember, this is an open string, right? Otherwise, it would be a funny non-local condition. So we would be saying that something that happens far, far away has to be locked to something that happens on the other end of the string. What sign? This sign. It should not be there, you're saying?
No, it should be plus.
It should be plus. Well, what you're saying is that this minus sign should not be there. No, well, doesn't this come from, I mean, it's just from evaluating the integral at 0, right?
Right, but the inside has changed. The inside
Oh, sorry. Yeah, what I meant to write was plus, plus, minus, minus. Yeah, okay, but I'm setting to 0 each part independently. Yeah, this is what I meant to write. plus, plus, minus, minus. Exactly the same thing that I had here. Yes. Yes. Okay. So next time, that's what we will do. Still, it looks very, very miraculous that we're going to get any spinors in space-time. Remember, all these guys transform as vectors, right? They have this vector index. Okay. So, so the next tutorial is when? Tomorrow? On Friday. Okay. On Friday, you will do more. You will study this theory more carefully, and you will discover that it has an extra symmetry that we didn't have before. Okay?
Question?
Yes?
Why was one of the plus minus signs redundant?
Oh, because remember, in the usually when you have fermions, right? The overall sign is something that doesn't have a physical consequence, right? So you can use that sign to eat up one of the signs. That's exactly the same origin, okay? But something else that I want to say is that tomorrow and Friday, there is something that happens. There is something that happens every 5 years at PI that involves all the faculty, and somehow I have to be there. So Lilia, who is one of our postdocs, she's an expert in supergravity and many other things. She will be the one giving the lectures. So she's going to change topics a little bit. She's not going to continue with this, okay? What she's going to do is to start out. Remember, we started the lectures last week discussing n equals 8 supergravity in 4 dimensions, right? Saying, well, could we have a field theory in 4 dimensions that is a theory of quantum gravity? So we added supersymmetry and so on. Remember, we also wrote down the spectrum of n equals 8 supergravity. And it was a very complicated spectrum with 70 scalars, tons of gravitinos. Well, it had 8 gravitinos, tons of gauginos. Now, when people tried to study that, people found that a simpler way to study that complicated theory is actually to think about that theory as coming from a theory in higher dimensions. Okay? So you did your study of spinors yesterday. So a nice exercise for you would be to try to find out in how many dimensions. Remember, the higher the dimension, the dimensionality of the spinors grows like what? Grows like? Yeah, roughly like 2 to the dimension, right? So if you want to have a theory that is supersymmetric, remember, when we did n equals 8 supergravity, we had to have one physical state that was a boson for every physical state that was a fermion, right? So if you try to do that, you will realize very soon that as you increase the number of dimensions, right, the number of degrees of freedom in a single fermion will very, very soon kill you. It will tell you that it's impossible to write something that is supersymmetric, right? Because it will be so big that you won't be able to match it with a number of bosons, okay? So the same constraint that in 4 dimensions gave us that you could only go from 2 to -2 in order to have gravitons would tell you that when you go in dimensionality, the highest dimension that you can have is 11 dimensions, okay? Just from that requirement. To write a supersymmetric theory, you will have to go, the maximum that you can do is 11 dimensions. So the maximal supergravity that you can have in 11 dimensions has only one supersymmetry. And that supersymmetry is governed by a spinor, right, that has 32 components. If you try to go to 12 dimensions, there will be no way to write down a supersymmetric theory. So for supersymmetry, 11 dimensions is somehow a critical dimension, right? For no reason, just it's an algebraic condition, right? Well, there is a reason, which is just algebraic, okay? So there is a constraint on the number of dimensions where you can do that. Now, if you take that theory and you do Kaluza-Klein compactification on a torus, you end up with a theory in 4 dimensions that has 32 supersymmetries. Here, by supersymmetries, I really mean the components of the spinors, right? So in 4 dimensions, the spinors have 4 components. N equals 8 supergravity has 8 supersymmetries, has 8 spinors. So 8 times 4, 32. So those 32 might be related to the 32 that I'm telling you about. In fact, what happens is that n equals a supergravity in 4 dimensions is the reduction on a torus of this unique theory in 11 dimensions, where you have a single spinor. So you have only one supersymmetry. In 4 dimensions, you have 4 supersymmetries. So you can imagine that just handling the objects is much simpler in 11 dimensions than doing it in 4 dimensions. As a tool, it's much better to do it in 11 dimensions. So people actually do that. To do computations in 4 dimensions, sometimes they think about the 4-dimensional theory as a dimensional reduction of the 11-dimensional one. So what Lilia will do is to show you how to start. She will write down this theory in 11 dimensions and show you how to do just a single compactification on an S1 to get supergravity theories in 10 dimensions. Okay? You would say, well, maybe we're wasting our time. Why are we doing that? Aren't we supposed to be doing a string theory? Well, we found in the bosonic string that we had this theory living in 26 dimensions, right? It was a gravity theory in 26 dimensions. With some luck, we're going to complete the construction of the supersymmetric version. So in the tutorial on Friday, you will find that this action is supersymmetric, and it's called superstring for that reason. And exactly following the same steps, we will find an action that is not going to be that action there. It's going to be a supersymmetric version of it. And it's going to live in 10 dimensions. Okay? So the strings somehow, or the super version of the strings, will prefer 10 dimensions as its critical dimension. You would say, well, it's not that surprising. I mean, it's not that nice because supersymmetry wants 11 dimensions as being the critical dimension, not 10. So it's like the strings didn't really get it. I mean, it would have been more surprising to get exactly 11, right? But, well, that question bothered many people, and in fact led to something very, very interesting that we're going to discuss next week. But the point that I want to make is that what you're going to do tomorrow and on Friday is going to be very useful for what we're going to do in the following week. It looks independent now, but the two things will coincide, will merge at some point next week, okay? Long story to just to tell you that you should pay attention to what you're going to do tomorrow and on Friday.